Welcome to Jason Kawalec's Capstone Masters Defense. It is my extreme pleasure to introduce Jason. I first met him back in January, February of 2020, right before everything went sideways, when he interviewed as an Arresti student for a summer position with me. And clearly things did not go as planned that summer. So there was a lot of changes, but what I've learned with working with Jason is he's able to just keep working and making progress despite pandemics and remote learning and all of that. So Jason has done excellent work over the last 4 years, really diving into the technical part of this and learning it himself and taking the courses that he needed in order to understand this. So I'm super proud of you for all that you've done. And not only does he have one job lined up, he has 2 jobs lined up after this. So he'll be working for the USGS this summer as an internship, and then he has a full-time job with the Department of Defense starting at some point in the future once the clearances go through. So he's only on to bigger and better things after here. So Jason's going to talk to us about the work that he and myself and some other colleagues have done in Costa Rica. Which he got to go to Costa Rica twice to collect this data. So please, Jason, take it away.
So welcome, good afternoon. Thank you for coming to my talk on my capstone. So the title is Applying Structure Motion Photogrammetry to High Resolution Terrain Modeling of Barva Volcanoes, Southeastern Parasitic Cones. So first, Barva volcano is one of many volcanoes in the Central American volcanic arc, which extends from southern Mexico all the way to Panama. And specifically, Barva volcano is one of the volcanoes in the Cordillera Central massive, alongside Poas, Turrialba, Irazu volcano. And these other 3 volcanoes are active. Irazu last erupted in 1995. Turrialba and Poas have been erupting within the past few years. Whereas Barva, the last confirmed eruption was about 6,000 years ago. And there were some historical reports of eruptions in the 1700s, the 1800s, but they haven't been confirmed. So there's been many more studies done on these other 3 volcanoes compared to Barva due to its recent inactivity, and as well as the fact that a lot of its northern flank is extensively vegetated. So zooming in now to a satellite view of Barva, and here's San Jose, the capital, the Central Valley outlined in blue, and the extent of the Barva Formation outlined in red. And the Central Valley holds about 65% of Costa Rica's population. And the extent of the Barva Formation from the geomorphic landscape view, the furthest extents of it are covered by the Tier B Formation, which is the result of the most explosive pyroclastic event of Central Costa Rica that is attributed to the Barva caldera. And the caldera is located here with the lava flows in brown and the craters in red, as well as the light green representing where tephra has been deposited. So to get an idea of Barva volcano's structure and lithology, here's a cross-sectional cut. Barva is an andesitic composite complex volcano, so it's had both effusive and explosive eruptions. It has several dozen summit cones on the summit, and specific, it also has several parasitic cones. So parasitic cones are cones that are on the flanks of the volcano. They're not part of the central vent of the volcano. So one parasitic cone in particular, the Monte de la Cruz cone, has been associated actually with this Los Angeles lava flow, which was dated to within 15,000 years ago. The Tier B Formation runs on the entire Barva Formation, and we don't have firm constraints on ages of the formations below this. Petrographically, the lava flows are primarily andesitic pyroxenes and basaltic andesites, as well as some olivine basalts and basites. Sure. It's going to be a process. I think. Okay, great. So zooming in further to just Barva's southern flank. Here is a topographic map on the left of Barva's southern flank. The summit volcano, some of the volcanoes here, and the slopes directly beneath the volcano have been mapped with LiDAR. But we see these two areas that have not been mapped to any extent. So specifically, I'm focusing on these 5 topographic bumps or hilly features that you see. And actually, this here is Monte de la Cruz, which has been confirmed as a parasitic cone of our volcano. And what we notice actually is that there was a study and they recognized that they all fall in this similar structural alignment here. So it's been hypothesized that this could be indicative of a shared origin between these cones. It could be a volcano-tectonic fracture that links them, or another hypothesis is that magma was coming up from a nearby contact between formations and generated these cones. So again, here are my study areas. These 6 cones, we actually, 2 years ago, we traveled to Costa Rica to image Cona Villadelia, Monte de la Cruz, and Cona Turales. And this last summer, I went back and imaged Cona Alto, Cona Villadelia, and Cona Rey, Cona Turales, and Cona Sinagas. So the Monte de la Cruz data is from 2022, but all of this other data, we went back with our drone in a real-time kinematics unit for higher accuracy positional data. So with that being said, the objective of this project was to model the morphology of the suspected volcanic landforms and therefore inform the chemical
Hey Siri, what's the weather outside?
your targeted field work for a comprehensive hazard assessment at Barva. So I have 3 sub-questions, being how well does structure for motion model the morphology, or how well can we use it to model the morphology of these features, and where instead might a more expensive LiDAR survey be required. I also had another question of what are the best practices for using SFM for estimating terrain beneath canopy, and to what extent can we confirm or negate this idea that these landforms are indeed volcanic cones. So last July, I went to these cones in Costa Rica with an RTK unit and a drone. So the general procedure that I went through was to first set up the GNSS base station to collect continuous positional data from overhead satellites. Following that, I then went around the cone and evenly distributed, or as best as I could, evenly distributed ground control points. So that's this map right here. The idea of ground control points is that they can be used to georeference the resulting model to a real-world coordinate system, because I'm taking precise measurements of the location with a GNSS receiver. I also collected checkpoints or ICPs, which I basically used to quantify the model's vertical accuracy because they weren't tied into the model georeferencing. And finally, the last step was to actually fly the drone and collect the images. I would use a pre-programmed flight grid, and the drone would take images at regular intervals, and they all have to be overlapping images because it's very important that the images are overlapping for the effectiveness of the technique we use, structure for motion photogrammetry. And this basically operates on the principle that you can derive 3-dimensional measurements from 2-dimensional images. So the structure for motion software that we use is Agisoft Metashape. And the idea is that it basically matches feature points between overlapping images to reconstruct the camera positions and therefore the geometry of the scene that was imaged. So basically I would come in with between 120 to 360 images, and I would align the photos. What that does is it matches the feature points into a point cloud of tie points. And in that step, I remove the points which have a low reconstruction uncertainty. And that refines the positions of the cameras and therefore allows us to generate a dense point cloud from which you generate depth maps, which represent basically the depth of each camera to each pixel on the images that I took. I also imported GCPs when I was creating the sparse point cloud. The sparse point cloud would contain between tens of thousands to hundreds of thousands of points. Dense point cloud would contain about tens of millions of points usually. And then finally, the actual results that I was most interested in interpreting from the dense point cloud, you can create a digital surface model, which is a continuous surface which represents the elevation values of the scene that you imaged. So the digital surface model, importantly, does contain overlying structures on top of the terrain, so it doesn't take those out. That includes trees, buildings, and another product I was interested in making was the orthomosaic, just for context with the digital surface model. The orthomosaic just represents the all the images sit together onto the surface of the digital surface model. So here are the results for just digital surface models. The warmer colors represent higher elevation values, and the cooler colors represent lower elevation values. I also outlined the general shape of the cones. And I divided them into two categories of partially open canopied cones and densely canopied cones. So the partially open canopied, I noticed that there was pretty intermittent tree cover, meaning that there is ground as well as tree cover on the summit of the cones, on the flanks, so you can perceive their general shape. Whereas with the densely canopied cones, there were very few spaces between or gaps in the canopy to see the ground. So that'll come into importance later when I'm talking about estimating the terrain of these surfaces. And I also want to note that in green and blue are the horizontal resolutions and vertical accuracies of the digital surface models. So 2 years ago, when I made the models without the RTK unit, we just had a handheld GPS. The accuracy, the vertical accuracy of those models was about, at best, like 5 meters of the elevations. So compare that to what we measured this past year with the RTK unit for higher accuracy positional data. We were able to constrain vertical accuracies lower than 131 centimeters to 15 centimeters. So here's just a closer up look at Naturalis, one of the partially open canopied cones. And you can note that we were able to pretty evenly distribute the ground control points as these white squares and the checkpoints as these red dots. And then here again, closer up look at a densely canopied cone. The entire cone is pretty densely covered by trees, with the only gaps in the canopy being perceived as just darkness because there's no light going to the surface of the or going to the ground of the cones. And yes, so the next step, therefore, was to try to model the terrain from these photogrammetric digital surface models. So here I'm testing 2 methods to estimate terrain surfaces and develop approximate digital terrain models from the digital surface models. So both of these methods I use, they both try to classify the photogrammetric products, and then from that classification, try to generate a digital surface model, or sorry, a digital terrain model from it. So this first method I used was that the Agisoft Metashape. It's built into the program, and it uses the 3D point cloud to make its classifications. So the actual algorithm that it uses is closed source because it's a proprietary software. So we don't know too much about how it works. All we know that it's a triangulated irregular network densification algorithm as referenced by Axelson. And basically how it works is it tries to classify each point in the dense point cloud as either ground or non-ground. So you give it several parameters to use, which I'll discuss. And once it has that classified point cloud, it uses an inverse distance weighting interpolation between the ground points to smooth out the surface between ground. And that sort of gives you a resulting approximate digital terrain model. Then the random forest method instead uses the digital surface model and the orthomosaic to make its classifications. So random forest is an open source machine learning algorithm, and it
you give it training areas, you identify several areas on the images or on the images, but on the digital surface models and the earth mosaics where you know it's tree cover or you know it's ground, and then you run the algorithm and it will learn from those areas to try to predict where it can know is now tree cover and ground according to your training areas. And then following that with the classified surface of tree cover and ground, I then subtracted canopy height from the tree cover classed areas. The data set I used was the global forest canopy height data set from spaceborne LiDAR. This was the best approximation we could find for canopy heights. So here's the classification, the classified dense point clouds. You can see that this entire area here, there's very few ground points that the software could identify. And similar here with random forest. And then the actual classification parameters that you give it for Agisoft, there's the max angle that represents it's an assumption for what the maximum slope of the ground is. The max distance representing the maximum variation in elevation that is still considered ground. And the cell size represents the area of the image of the dense point cloud in which there is at least one ground point. And these are the training areas that we use for these two cones for the random forest. So here are the results of the approximate digital terrain models. And one immediate observation I had with the partially open canopied cones for the Agisoft method is that they pretty well constrain a cone-like morphology for the partially open canopied cones. And that's in contrast to the Agisoft method for the densely canopied cones. You see that there are these spikes in the resulting digital terrain model, and that's due to the fact that there are so few ground points available for the software to interpolate between, that it produces a lot of artifacts in the resulting digital terrain model that don't necessarily represent a cone. With the random forest results, we see that they still look very similar to digital surface models, and that's simply because we don't have the data to accurately account for the variability in tree elevations because of how much the elevations of the trees vary. So while the elevations of the trees have been subtracted, there still is that effect of all of the elevations of the trees varying. And here is a closer-up look at an approximate digital terrain model for Cone naturalis. And you can clearly see that the cone extends a little further to the southwest from the digital terrain model. And again, Agisoft clearly more represents a cone than the random forest method. And with the densely canopied cone of Philadelphia, we see that there are several spikes that represent a few ground points that the Agisoft was able to locate, but neither of these digital terrain models would represent the terrain of these cones. So here are my, and also another way of visualizing this data was to create elevation profiles. So here are all the cuts of the elevation profiles that I made. And for additional comparison, I compared my elevation profiles with elevation profiles from this previous highest resolution digital surface model. So it's a regional digital surface model created by aerial images from 2007 at a coarser resolution of 10 meters per pixel. It's also important to know when comparing these elevation profiles that the elevations of the trees were likely lower in 2007 when the images were taken than they are last year when I imaged these areas. So here are the results of these elevation profiles. And the blue line represents the 2007 aerial digital surface model that I just mentioned. The orange line represents the Agisoft terrain model, and the green line is the random forest. So one observation I had for the partially open canopied cones is that the Agisoft digital terrain models actually more closely represent the terrain or the actual true terrain than the 2007 aerial model does. I know that based on my physical experiences traveling these cones and observing their shapes. So for example, cone array, which while it is a very small cone, is associated as an extension of the Monte de la Cruz cone. It's much better represented by about 20 meters of topographic change compared to the digital surface model, which only indicates about 5 meters of elevation change. And then also with cone naturalis, we see that this area here, which is represented, is mainly covered by trees. And the digital surface model, of course, takes into account the trees from 2007, whereas the AgiSoft terrain model was able to interpolate between the ground points on either end of the tree cover area, and therefore create a more smooth terrain model of the cone, which more represents a cone. And then with the densely canopied cones, we see a lot less agreement between the elevation profiles. And that again shows the difficulty in creating terrain models from photogrammetry for these densely canopied areas. So here we see up close cone of Philadelphia. You see that this one spike is where AgiSoft was able to identify a few ground points, but that's all it had. That's all the data it had to work off of. So it isn't able to actually resemble a cone-like shape. So here are the conclusions that I've been alluding to, comparing the terrain approximation methods. So I've concluded that structure for motion is sufficient for effective terrain approximation with the use of the AgiSoft method. And I noticed that one important factor for that was that AgiSoft can interpolate effectively when the ground is distributed on the summit, on the flanks of the cones. And another just important note is that with these partially canopied areas, that the ground control points and the checkpoints should be evenly distributed across the canopy openings as possible for the vertical accuracy of the resulting models. And then for the densely canopied areas, I concluded that while random forest provides an approximation by lowering the canopy heights, both methods overall are insufficient for accurately representing the terrain of these areas. And for AgiSoft, I concluded that this was because AgiSoft cannot interpolate effectively between very distant ground points to represent the terrain. And for random forest, it suffers from the lack of high resolution data on the canopy heights in order to subtract it from the trees. So yeah, so in terms of the geological implications of this study, they're certainly limited right now, but this is part of a larger effort to model these cones, so there will be more to come. So one thing actually that I noticed though with the digital terrain model of cone of Philadelphia is that when we were in the field, we located this kapuka. A kapuka is a raised area of land surrounded by lava flows, and that is easily distinguished in the digital terrain model by this raised area of green contours compared to the 2007 model. We don't see any significant elevation variation there. And then similar situation for Monte de la Cruz, but with its craters. So from the digital surface model, you can identify, based on the gaps in the canopy, you can locate these two craters that the Monte de la Cruz cone has, whereas in the 2007 model, you don't see any elevation variations within this model. And it's possible that this is either due to the cones being covered in 2007, or just that because this 2007 model is a much coarser resolution, it's not able to resolve these changes in the topography. And as I said, this work is part of a larger project. So here's some ongoing work from courtesy of a student in Costa Rica who's mapping the lava flows associated with these cones. So specifically, lava flows are numbered and they're shaded differently. You can see there's the kapuka that I mentioned there, and here's cone array, really north of Monte de la Cruz. In terms of the limitations of this project, in the canopied areas, we were unable to evenly distribute the ground control points and the checkpoints, which does lead to a spatial bias in our resulting measurements of the vertical accuracy, such as here at Cono Alto. And another limitation for reproducibility of this study is that the weather dramatically impedes the surveying and any drone flying because of low cloud cover and high winds along the mountains. And another limitation for reproducibility is that we were fortunate to have a ArcticGate setup constructed by Dr. Schmeltz on a budget, but normally this would be a commercially expensive setup. And another limitation is just that both of the terrain estimation methods that I'm showing have shortcomings for the densely canopied areas. So here are my overall conclusions. As an outcome, I produced digital elevation models for these 6 suspected parasitic cones at higher resolutions and higher vertical accuracies than the previously developed digital elevation models. I also demonstrate the effectiveness of the Addisov Metashape ground filtering algorithm for partially open canopied areas in approximating the terrain. I show some best practices for future work in applying structure for motion to canopied areas. And I contributed some morphological evidence to support the claim that these landforms are volcanic cones. In terms of future work, for Barva's southeastern flank, we concluded that for the cones that we weren't able to model the morphology of the densely canopied areas, we suggest LiDAR surveys of these areas. And the idea is that once we have all the terrain models, they can be combined with the ongoing processing of geochemical samples for a comprehensive hazard assessment of Barva volcano. And then also this methodology can be applied to several different areas in Costa Rica, which are similar geomorphically, where the terrain is not mapped at a high resolution. So one example is the Aguas Zarcas volcanic field north of Huas volcano. And these cones actually look very similar. Suspected cones look very similar to the cones that we examined in this study, but they haven't been mapped at a high resolution. So there are plenty of other areas where a similar methodology could be applied to different areas in Costa Rica. So yeah, I'd like to acknowledge the Institute of Earth, Ocean, Atmospheric Sciences for funding, as well as the Sparks grant from the Department of Earth and Planetary Sciences. I'd like to thank my wonderful mentor, Dr. Lauren Adamo, because she's given me so much of her time. We all know how much she does for the department, but she's given me so much of her time, her mentorship, her support, and helped me find my passion. So I'd also like to thank Dr. Schmeltz and Dr. Oja for their insights in remote sensing and their teachings over the years. Thank you to Dr. Paolo Ruiz, who is online right now, for guiding my field work, and also for contributing the volcanological insights for this project. Thank you to my parents for being my research assistants in Costa Rica. Thank you to my brother for being my brother and supporting me. Thank you to my girlfriend Gemma for support and love. And thank you to anyone I haven't mentioned that's supported me throughout this process. So thank you, and I will take questions. Yeah.
What about any ways to get around some of those problems in density areas?
Yeah, I think with photogrammetry, there's different, there are other methods that I haven't tried, such as there's one method, it's called where you simply try to remove the vegetation like a blanket over the surface. So I haven't tried that yet. I would be interested in trying that. It's available, I think, in this other software, Cloud Compare. But I think with photogrammetry, you are limited to your possibilities in terms of actually modeling the canopy, or sorry, modeling the terrain under canopy, simply because they're not visible within the images. So that's why we're thinking of, I think in the future, just suggesting that LiDAR would be better equipped to handle these areas. Even though it is more expensive, it can penetrate those gaps in the canopy where there's just leaves or shrubs, and try to reach the ground surface to actually model the terrain underneath.
To follow up on that last question, I was thinking when you're doing that, can you just apply some sort of filter, that averages out the canopy areas? I mean, I don't know how much variation the canopies are in meters or. So if you just.
Yeah.
Yeah, you at least maybe a better.
Yeah, so actually that was the other method I tried before using this other data set, was to measure the average height of the trees within each study area. And the problem was that the trees just vary so much in height. I'm sure there should be some way to do it where it's just so difficult to know the heights of these trees when they're so far from any ground surfaces. So yeah, for this cone where almost this entire area is trees, like it's almost impossible to accurately measure the heights of these trees in here because we don't know the ground surface.
Is the tree height vary area to area? Or
Yes, it does also as well.
that's the problem.
Yeah,
It's all 20-meter trees or something.
Yeah. yeah. So I think it gets slightly lower moving up the flank of the volcano. So it ranges from about 10 meters to 20 meters. But yeah, that's another problem with.
There's also the really tall shrubs on the side.
Yeah, there are some very tall.
It's the rainforest. It's tall.
Yeah, no, if it's all tall, then it's okay, but if it's small.
How much of that variability in height is a function of just the kind of plant it is, like from the image, if you have means of classifying
Right.
what kind of plant that they're aware and seeing some height, right? Yeah.
Yes, that was also a suggestion. I think the problem with that is that the maturity of these trees is also very different. So even if you could identify the species of these trees, even then they still maybe be at very different heights. But that is something that we talked about, that you could in the field note down the different species of trees that you're observing in the area.
While you're on this,
Oh, yeah.
what are those popcorn features
Here?
Yeah, what is it called, those?
So that is sort of a product of subtract of the tree height variation. So so the data set I'm using, the 30 meters per pixel, it'll cover this entire 30-meter area with the average height of the trees in that area, and then subtracting it by it. So some trees it completely eliminates, but some trees that are slightly lower than the average height of trees in that area, they end up looking like pock marks in the ground. And this was actually a worse problem when I used the average height of trees, because some trees here, like on the cone itself, are much higher than these lower lying trees on the perimeter. Yeah.
What's the process of like going out to it? It's like, did you need permits? Like, were people receptive to you?
Yeah, that was a fun aspect of this. Yeah, generally for the parks like Monte de la Cruz, we would ask the park managers, and the park rangers, and they were fine. And pretty much everyone we asked when we were going around these places was like, we just had to explain to them what we were doing and trying to map. And they were pretty receptive. But yeah, in some cases where we had to travel on private property, we'd be approached by the homeowners, and we'd just have to explain to them what we're doing.
So if you were to continue this, would that be too like?
No, I don't think so. Everyone was pretty receptive, yeah.
And that what happened. With the owner, he was really thrilled. with
Oh
it.
yeah, actually, yeah, some of the people on the private property that we would go to, they were very excited actually to be involved in this study and have their homes, I guess, be on volcanoes, I guess, because it really isn't, the people here really don't know that these the hill they're on is part of the volcano. They think the volcano's all the way to the north.
How did you identify this? Before you even had that?
With the help of so this was, I think, identified from the topographic map where these where we see these topographic features. Again, Monte de la Cruz, we already knew, because it has these distinctive craters, we knew it was a cone. But with the help of Dr. Paulo Ruiz in Costa Rica, he sort of identified these features first as cones.
You see different kinds of plants that are growing on these cones versus elsewhere, and could that be used in terms of future identification?
Yeah. You mean like along the slope?
Just on the cones themselves.
I mean,
What's
like-
growing-
Oh.
yeah, the plants, yeah, what's growing there versus what's not there.
I don't think significantly. Again, there are so many different species because this is a rainforest. I mean, just looking. Yeah, I'm not like a botanist, so I wouldn't know fully, but I would think that most of the species are also being observed, both on the cones and off the cones. But that would be interesting if certain,
Change in the composition.
right, if the soil is more fertile, yeah. Yeah.
So, good one. You know, it was difficult to identify the canopy height, but do you feel like the random forest method accurately identified where trees were, and did it do a good job of identifying maybe where small areas of ground were within the image, or within the area you surveyed?
Yeah, I think, so generally, yes, it did do a pretty good job of identifying ground. I think that with some of the areas in here on the Cone of Philadelphia, this was the densely canopied one. There were a lot of areas that were incorrectly classified. I think that's partially due to the difficulty, and I had considered, tree cover as, from the smallest trees to the tallest trees. Some of them look very different, and they also could be confused with shrubs, other low-lying vegetation. Yeah, I think.
Just to follow up, so is tree cover in this classification is inclusive of shrubs, or?
No, but even then it would still get confused. I think like on Conaturales, where the summit was had some tall grass on it, it would get confused as well.
Since he's already asked it, and this was one of the questions I was going to ask, how would you better train random forest? Would you see that kind of things you think about?
I think I would make a class for just the shrubs. I think just the difficulty is even looking at the ortho images, that it's difficult to distinguish myself to make those training areas for shrubs versus small trees. I think you could do maybe tall trees, small trees, and shrubs. I think that would provide some more information for the algorithm to differentiate between those.
And the second question, this sort of, don't think this wrong, I'm just saying, why is the recreation of these small cones important?
Right.
I'm not saying here.
No, yeah, absolutely.
You know what I mean? There's a question of why.
Yeah, why am I doing this? Yeah, absolutely. So this was primarily motivated by the need for a hazard assessment of this slope. A lot of these, like Cones and Yangas in particular, there's a lot of people living on this cone, and they don't even know that it's a volcanic cone. So I think not only providing that information, but to eventually come to a point where we've dated the lava flows surrounding these cones, where we can possibly identify any possible volcanic vents that we even now don't see on these cones. I think that would that strongly motivates the need to inform the people living on or nearby these cones of the fact that they're living in volcanic terrain.
Okay. So Matt has a 3D prints of each of these cones and like to see them, that's what we worked on this year. But it's fine, we can, if anyone wants to see them, you go ahead.
To follow a little bit up on Carl's question. Aren't these cones like really supposed to be like fault lines, right? I mean, that's why they exist. I didn't know anything about parasitic. But that's what the idea is, right? So by knowing the distribution in space better, can you then do a more of a structural map as to of this area?
Yeah, so I guess the only like pitch there is we don't fully know if it is a fault that's linking these cones. Because it could also be that there are several, I think there's a contact that runs off this map that runs parallel to this. So the magma could have come from that contact between formations. But if it is a fault, then absolutely, I think this would be a further step of the study is to look at more of the structural geology and understanding these the features that link these together.
Paulo has his student doing the field map and then, I mean, have you been here before? The vegetation is just insane and the weather is insane in tropical areas. So there are places when you dig into the hill and it's just soil and you can't even get a fresh sample. So it's really wood intensive to get down to the actual geology. So, but hopefully Paulo's student Andrea will have some of this in the future.
Yeah, I remember my car bringing that sample, we're gonna get a core of the boulder, you know, because
Yeah.
it's so much weather.
Yeah.
And they were all recent too, they weren't like really old. But I don't know, it's intense.
When I went to Costa Rica with my car, he took us to this outcrop and it was white. And he asked us what it was, and I had no idea, because I think it was salt. I was like, no, it's not. And he like scraped down, and sure enough, it was like black. But yeah, it's weathering and vegetation like you've never seen here in New Jersey.
I feel like to do this really properly, you would, I think, really need a LiDAR, right? So
Yeah.
how much more expensive is LiDAR compared to like the photogrammetry tools that you're using right now?
So this whole setup, it's be probably, I'm not sure about, maybe a little more than $2,000. The mainly being the drone, and that's including John's very inexpensive RTK setup. With the LiDAR drone, I've seen them go for more than or about like $10,000.
50,000.
Way more. Okay, yeah.
With the LiDAR and the drone.
Yeah, so they have LiDAR, they're octocopters, right? The bigger ones with the built in, and then they have the software that comes with it. So I got it quoted about 50,000 or more, depending on. So yeah, it's a significant increase.
Components are less,
What?
I think the individual components are less expensive.
You building this on.
Yeah, I mean, you do 5,000 versus 50, 60,000.
Is there a region nearby that's a little more arid enough to apply these to the less vegetation and, you know, in that area to well, it's so different like you do, but
I guess then you, I mean, the further down the slope you go, then you may come into the problem of more housing. But there's similar, so you're asking, are there similar areas where it's just terrain that we can compare?
yeah, well,
That's you.
satellite phones are kind of, you know.
Yeah.
Just the height of volcanoes, I this area, but it would just seem like, it'd be a lot easier to use with less vegetation.
Yes,
So-
absolutely.
So in other words, you do that.
Yeah.
And look at the differences. That compare that to something that's-
Yeah, so I mean, so there's a recent eruption in 2021 in one of the Canary Islands, La Palma. Let's see. Oh, yeah, so we actually see a lot of the similar features, and yeah, because it was a fresh eruption, there was no vegetation, so you could there was a project that mapped the cinder cones that resulted from the eruption, and it's much clearer to see it as opposed to dealing from the digital surface model to the terrain model. So yeah, that would be an interesting comparison. One of the sort of like things I was hoping to do eventually was to compare some morphological parameters like the slope, the basal diameter of the cones, with features that we know are parasitic cones.
So asking if there's any questions online.
Yeah.
Sorry, so do you know if anyone has done this with LiDAR in this environment? Just I know that I've done some work with airborne LiDAR. I'm just around here for the beach, but sometimes that doesn't get through dense vegetation and
Yeah.
that's just like shrubs maybe a meter or two by. I didn't know if anyone has kind of tried that in this environment and kind of had a successful result. So just in terms of answering that comparison,
Right.
does LiDAR provide an improvement?
I didn't come across any studies.
Wasn't the one Paulo did, wasn't that smaller area?
Yeah,
of
that's
LiDAR?
I believe that's a small area directly below the summit cone from airplane LiDAR. Yeah, is there anything else in the question?
But did it produce a kind of a better result?
Yeah, I don't think I've handled that data myself. I want to get more into using LiDAR data, but I haven't sort of launched into that yet. But
Just to address on substantially. So like in Amazon, they found all these ancient pyramids that no one had known about by using LiDAR. So if you have massive volcanic vents, parasitic cones, easy peasy.
I talked to Paulo and it said that they have to justify the use of LiDAR, right? So because of the cost and stuff, so they get funding to do smaller areas, and it's mostly due to landslide hazards is where the funding for that comes from, so. Paulo wants to know, can you mention a little more detail the difficulties due to weather that you faced?
yeah, and flying the drone. Yeah, so it was certainly very challenging. I mean, ideally, with the idea of weather, like on this day I think even on this day, I was waiting for the clouds to pass, because there were clouds directly over. But yeah, here there was a Monte de la Cruz. We went there, but we couldn't re-image it, because of the high winds in this area particularly. So not only were there significant high winds across all of the cones that we were trying to survey. They was kind of just waiting for a day that was a miracle of just sunshine and calm weather. And we got that 4 or 5 days of about 2 weeks that I was there last year.
Joseph Kawalec, which is your brother. It says awesome presentation. Apologize I missed this, but did you consider any classification algorithms other than them?
Yeah, so I think that's a future direction for the project. I personally didn't invest time into that, but I know there are several other classification algorithms. What's the other? Well, it's similar to random forest. I just know that there are. I'm blanking on the ones I'm thinking of right now, but neural network I know is one. Yeah.